All right, well, hey friends, welcome back. Happy Monday. We're in that last little push before Christmas break. So I know I brought this up Thursday. I think it was the day it was. So we are kind of doing notes on rate laws today and tomorrow. This is some fairly heavy math stuff. So make sure that you have a calculator handy somewhere. Mine just walked away. Especially tomorrow, we're going to be needing to use some of the stat functions. So if you have a graphing calculator, that's great. If not, I'm going to show you how to do it on Excel or Google Sheets if you don't have a graphing calculator handy. That way you're still able to do some of the applications. Wednesday will kind of be a review day to practice, ask me questions. I did not have time to go through, excuse me. I didn't have time to go through all the book questions and separate them out day by day. But I did post them up here for you guys. That way you have some additional practice, and I'll look and see what else I have. Thursday, we voted to do notes, even though that will not be on this quiz, and our quiz is going to be on Friday. So that kind of gives you an extra day. If you have any of those leftover questions, I'll address them. And then next week, we're going to review the notes from Thursday, maybe do a little bit of practice, and start on our kinetics pre-lab for our lab that we're doing next Tuesday. You'll have a cumulative quiz next Wednesday, and then our test is next Friday. So we'll actually be done with notes this week, but that gives you some time to practice, ask questions, things like that. And then remember that week we get back from break, or whenever people have teacher-made exams and stuff, and we'll do our midterm that week. So that's kind of where we're at. We are going to, hang on, I gotta switch screens. All right, let me switch screens with both groups real fast. Yeah, Addie, our midterm will be on the Thursday. I think I'm still trying to rework it because we have a slightly shorter time period than we normally do. But you should have like a multiple choice part, which I can open up early, and then a short answer part. But I'm still reworking it and trying to figure out how I want it formatted. And kind of how much time I want to give you guys. I might give you the whole thing early and just make it do that Thursday. I haven't fully decided yet, but we're kind of getting there. So what we're going to look at today are reaction rate factors and reaction rates in general. This is something that you may or may not have gotten to in Chem 1, depending on when you took it. I know my guys that took it in the spring here, you only really got a couple of days of this, but we don't do too much of this in Chem 1 anyways, so you're not missing anything if they didn't get to it. We are going to go over everything. None of the math was done in Chem 1, so that's new for everybody. So this unit is going to be fairly new content that you may have never had exposure to. And we are going to finish it up before break. Like I said, it's not a ton of notes. We are going to finish up notes this week, but it is a lot of math. So that's one of the things that kills people a lot of times, are the math. So just make sure you're kind of following along with me. I did post all of the notes so that we can get through those together. So ways that we look at reactions are in terms of stoichiometry, thermodynamics, which is actually our next unit we're going to go over. You guys did a little bit of thermo in Chem 1. So in stoichiometry, we basically looked at the reacting ratios, the mole ratios, limiting and excess reagents. In thermo, we tend to look at how heat changes during a reaction. And if a reaction's spontaneous, you may have never heard of that before, but that's kind of what we're getting into next unit, and it's actually in our last unit of AP as well. That content is split. But what we're going to focus on in terms of describing reactions right now is kinetics. This is looking at the speed or rates of chemical reactions. So how fast a reaction is going, looking at how much products are being created, how much reactants are being consumed, things like that. All right, so in terms of reaction rates, we're going to be looking at the rate is equal to the change in concentration over the change in time. So how much the concentration increases or decreases over a set period of time, whether it's measuring it over 30 seconds, measuring how long it takes for a color change to occur, things like that. So here's just kind of a base reaction. So it has a substance producing bromide ions, hydrogen and carbon dioxide. Now, bromine in itself is kind of an orange color. So it's going from that deep orange color to where whenever it's producing ions, it's going to be more clear. So as you notice, the color will change throughout the reaction. So the concentration is changing throughout the reaction. So if we were looking at the rate of bromine reacting, we said it's the change in concentration over the change in time. And for reactants, hang on, let me get my pen function. For reactants, these are being consumed. Which means they are decreasing. So that's why there's a negative in front of it. And it also accounts for the number of moles. So since there's only 1 mole of bromine, there's no number in front of it. So it's just kind of a -1 in front, looking at the bromine. In terms of the products, these are being produced or formed. So a lot of times it'll be the rate of formation. So that will have a positive number in front of the change in concentration or the change in time. So that's going to account for if it's being used up, it'll be a negative, versus if it's being created, it's going to be that positive number. So this is kind of what we would do with the spectrophotometer that we used in our Beers Law lab that we did measuring absorbance. This is another application of it. And we normally do another kinetics lab with the spectrophotometer. I'm not sure if we're going to do it this time around, but it's used to measure those different concentrations. And that can look at the rate of reaction. So you might mix certain concentrations together and see how long it takes for it to go from colored to clear and things like that. So here's kind of how kinetics. So this is using that same reaction. And it says, okay, at time 0, whenever we start, we have a concentration of bromine of the 0.0120 molar. And then it measures the concentration every 50 seconds and notes how it changes. So we would pick 2 of these values to find the rate between. So if we pick 0 and 50, and we could actually calculate this. So we said the change in concentration. Yeah, my calculator walked away. Let me grab it. So we would find this by doing the change in concentration. So that would be the point. 0.0120 minus 0.0101 over the change in time, which is 50 seconds. And since bromine is a reactant, remember that's going to be a negative in front. So that is how we would calculate the rate between these two individual steps. Now, if we picked two different time frames, we would do the same setup, but we would have a difference of 0.00353 minus 0.00296 over the change in time, which was yet again 50 seconds. And it would be negative because it's still bromine. Because it's at a different point in time, it can have a different rate. And note that this is negative because it's being consumed, being used up at that rate. So whenever you actually look at a graph of this, a lot of times it will be curved. So there are going to be different rates at different segments throughout the curve. So the average rate can be calculated for each individual time frame. The instantaneous rate is looking at the graph, the rate at an individual instant in time. So this is where we would actually have a graph and say, okay, at 100 seconds, what's the change in concentration over the change in time from 0? But instantaneous rate, they can actually look at a curve. So they would actually graph this out a little bit more mathematically. We're not going to have to do this based off of graphs. We're going to be doing it based off of if you're given data in a table, can you set up these formulas to find that rate between two individual points? So there's kind of an example of what they did at the 100 seconds. That's how they found it. Now, one thing to note is you can do this for other substances as well in the reaction. So if you know the rate of one substance, of whether how fast it's being used or formed, you can find the rate of everything else in that substance just by basic stoichiometry. So if we know the rate of bromine and we're looking at the bromide ion, one thing to note in our reaction is for every one bromine, there are 2 bromide ions. So we do have to account for that. So whenever we're writing our rate, it's going to be the same value, but this will be a positive rate because it's producing a product, it's being formed. And you always do kind of the inverse of whatever that coefficient is. So since there's 2 bromide ions, it's going to be 1/2 the change in bromide ion over the change in time. The overall rate is going to be the same, but it will be positive instead of negative. So you could figure out individual concentrations if you know the rate of one substance. We could also set this up for carbon dioxide. If we set this up for carbon dioxide, it would have a positive in front of it. The coefficient is 1, but it would be the change in carbon dioxide over change in time. So we can set this exact same thing up for every substance in this reaction based off of that same rate. But remember, for reactants, that rate will be negative because they're being used up. For products, that rate will be positive. So for the carbon dioxide, because it's the same coefficient as the bromine, it will still be the 2.96 times 10 to the negative 5th meters per second. But here, this is the rate of formation. For bromine, this is the rate of consumption. So you may also see this as a negative number to show that it's decreasing by that much per second. So here's just another example. If you have the reaction of A produces 2B, the rate of consumption for A, it would be the rate is equal to negative change in A over change in T. But for B, it would be a positive and do the inverse of the coefficient. So positive 1/2 times change in B over change in T. So factors that affect reaction rate. This is the one thing that is in Chem 1. So if you didn't get to this in Chem 1, this is really the only thing that you missed. But we look at what changes the overall reaction rate. So things that change reaction rate are concentration. I don't know what it's doing today. So in terms of concentration, generally a higher concentration is going to have a higher reaction rate, is kind of the general rule. So if we were doing a reaction with 1 molar hydrochloric acid, and then we did the same reaction, but this time with 3 molar hydrochloric acid, we would expect the 3 molar acid to react faster. We can also look at temperature. And generally, the higher the temperature is, the higher the rate of reaction. There are some exceptions, but that's going to be our general rule. So think of if you're trying to make sweet tea and you're trying to dissolve the sugar is going to dissolve faster if the tea is warm versus if the tea is cold. Same thing, a lot of times when we want a reaction to occur faster, we want something to evaporate quicker, we're going to pump up the heat on it. See, concentration, temperature, particle size is another one. And this is one that tends to confuse people a lot of time. So whenever I talk about particle size, if you have really small particles, so say little grains of sugar versus sugar cubes, the smaller particle size means that there's a greater surface area. So more places for reaction to occur, so it speeds up the reaction. So this is where if we were doing a reaction with crystals, we would want to like grind up the crystals into as small pieces as possible before the reaction, because only the stuff on the outside of the crystal would react, whereas when we grind it up, all the crystal is exposed whenever it's in those smaller pieces. We also look at pressure and volume. A lot of times these we deal with gases, a lot of times. But in general, it's looking at, are the particles being pushed closer together where there's more collisions with particles? The number of collisions is going to determine how fast the reaction rate occurs. So like with pressure, if it's a higher pressure or a lower volume, the particles are pushed closer together, so they will have a higher reaction rate. And then another one that we'll talk about a little bit later this week is if there's a catalyst. So that's one that you probably heard in Chem 1, even if you didn't get to that last unit in Chem 1. These tend to speed up reactions, and we're going to talk a little bit more about how they actually work and why they speed up reactions. So looking at rate laws, the rate laws is going to be a way to actually measure how fast a reaction is occurring. And if you change one substance, what that does to the reaction rate itself. So rate laws express the relation of the rate of reaction to the concentrations of reactants. So this one's based strictly off of concentrations. So if we had a reaction of A plus B produces C, our rate law looks at the concentrations of reactants. So our rate is going to be equal to K, which is a constant, times the concentration of A to some power, times the concentration of B to some power. So we're going to actually learn how to write these based off of data, how to figure out what that power should be to look at how that affects the overall rate of reaction. So K is our rate constant, and this is temperature dependent. So if the temperature of the reaction changes, that value for K is also going to change. The only thing that will change K is temperature. Nothing else is going to affect K. Those exponents are the order of the reaction with respect to each reactant. So there are some reactants that, if you double the amount of that reactant, it will double the rate. Sometimes it may not affect the rate at all if it's in excess or something like that. Or maybe it will quadruple the rate of the reaction. So that's what we're looking for, is if we change this concentration, how it affects that overall reaction rate. But those exponents are not based on the coefficients. We have to actually find them based off of data. So these are determined based off of data and determined experimentally.
How do I download a kid's stuff?
Hang on, guys.
From what? In Desmo, or not Desmo, in Dino. How do I download their history or their, other than just screenshotting what they're doing? How do I get it to where it?
I don't know. Hang on, guys. I'll hear it.
Sorry, Grace.
Hey guys, sorry, we're having issues. All right, so here's how we're experimentally going to determine this. So you're going to have data, and you're actually going to have to look at how much the rate changes in comparison to how much the concentration changes. So we said our base rate law was going to be the rate is equal to that constant, that K, times our two reactants, but we don't know what those exponents next to our reactant should be. So that's what we're going to end up finding out. So in order to find this, we need to pick data points where only one of our concentrations is changing. So let's look at the first two. During these first two, and I'm kind of going to draw a box around them. If you notice, B does not change. So I can use that data to figure out the rate of A. So what we do is we look at the change in concentration relative to the change in rate. So on one side of our reaction, we look at the change in concentration compared to the change in time. I don't know why I just put in brackets. That should be parentheses. So we're going to do the change in, or hang on, that's not right. It's change in concentration compared to change in rate, not change in time. I'm all flustered now. Okay. All right. So change in concentration relative to change in rate. So for change in concentration, we had 0.20 is our higher concentration, and it was 0.10. And then that is what gets multiplied by some exponent, which we don't know what it is. That gets compared to the difference in rate. So it was the 0.40 over 0.20. So whenever we simplify this, 0.2 divided by 0.1 is 2. On the other side, 0.4 divided by 0.2 is also 2. So we look at what does that exponent have to be so that 2 raised to some power is equal to 2. And your powers are either going to be 0, 1, or 2. So you're not going to have to deal with like every number under the sun. So 2 to the first power would be equal to 2. So x is equal to 1. So that means that this reaction is first order when looking at A. So that means that, and we'll go over what this means a little bit later, but if it's first order, that means that if A is doubled, the rate is also going to double. So they're going to do the same thing. If A is multiplied by 3, the rate is going to multiply by 3. We have to do the exact same thing for B. So let me change colors for us to do B. Let's do green. So whenever we're looking at B, we need to find where B's concentration changes, but A's concentration stays the same. So B's concentration, we can use these next 2 points because A stays the same, but B changes. And we always want to make sure to pick points, even if they're not right next to one another, that's okay. But if both variables are changing, you're not going to be able to find that exponent. So doing the same thing for B, we do the higher concentration over the lower concentration. So the 0.20 over 0.10 to the y power, which we're trying to find. And then we do this, the rate. So the higher rate is with the 0.20, so that's the 2.40 over 0.60. So 0.2 divided by 0.1 is 2. So 2 to some power and 2.40 over 0.60 is 4. So we need to say, okay, 2 to what power is going to be equal to 4? So 2 squared is 4. So that y is equal to 2. So that means this reaction is first order according to A and second order according to B. We can also find an overall order. Let me switch colors again. So overall order, you would add the exponents together. So this would be third order overall. But like I said, it looks at, okay, if I change A, what happens to the rate law? We said it was first order. So if A doubled, the rate also doubled. In terms of B, since it's second order, whatever happens to it is squared. So if you double B, the rate is quadrupled. If you do B times the third, the rate is going to be cubed. So it will kind of change that and alter that as it goes on. Another thing that we'll have to do is find that K value. And I may be getting ahead of myself, but in order to find K, you're simply going to pick one data set to plug into that rate law to solve for K. So let me do this in another color down below. We'll do purple this time. So I a lot of times just pick the first data set to plug in. So I would say that my rate is the 0.20 is equal to K is what I'm solving for. Concentration of A is 0.10, which was to the first power. B was 0.10, which gets squared. So I would simplify this. So 0.10 to the first times 0.10 squared. So I have 0.20 equals K times 0.001. We divide by 0.001. We get that K is equal to 200. The other thing we have to do is we have to figure out what is the unit of K. So we have to look at our units and see what canceled out. So if you look at our original reaction and what we had K times molarity to the first times molarity squared is equal to molarity per second. This is where it can get a little bit tricky. So whenever we divided, we have that K is equal to molarity per second over molarity cubed. Are y'all following me right now? This is a little funky. All right. So what happens whenever you have a fraction divided by something? Remember, it does like the, in my day, we called it the copy dot flop. They may say it's something different, but we had molarity times second times 1 over molarity cubed. So that molarity cancels, one of them does. So this will now be molarity squared. And they're both on the bottom. So the unit would be 1 over seconds times molarity squared. So that's one option for your unit. Your other option is to show that it's on the bottom. It just needs to be a negative exponent. So this can be molarity to the negative second, seconds to the negative first, to show that they're on the bottom. So that's something that's a little weird that does take a little bit more practice and going through. But that's kind of everything with finding rate laws and the rate constant. And we're going to talk about these some more, and I have some more examples too. So looking at what that reaction order means, like I said, if it just doesn't have a number next to it, it has a 1. That means that it's first order. Yeah, Addie, that's what like a complete problem would look like. A lot of times it will be separated into different steps though. So if a reaction is first order, or it may have a 0 next to it, so it can be 0 order. That's a possibility. We did not have one of those in our problem that we just did. Oops. So something like a phase change is going to be 0 order. So what it means whenever it's 0 order is the concentration does not affect the rate of reaction. So how much water you have is not going to determine how quickly water boils. That's not really a piece of it. Versus if we had a reaction like this, what we would say, looking at the rate, let me switch to the laser pointer so you can see. So the rate here in terms of the rate law is first order, looking at this kind of methyl group right here, and then 0 order according to hydroxide. So hydroxide is not going to alter how fast the reaction goes. So whenever it's 0 order, that does not affect the overall reaction rate. So this doesn't even have to be written technically. We could completely X this out and leave this out and just write this as our rate law. So what we're going to deal with a little bit later this week is sometimes these do not occur in one step. So what will happen is there will be one step that maybe splits apart a substance and then a second step that goes through the actual reaction. So we're going to talk about that a little bit more on Thursday with our different mechanisms. Because you may have a slow step and a fast step. That slow step is what determines your rate law. So it's kind of like if you wash your own clothes. You know, the whole process is you put clothes in the washer, wait for the washer to wash them, then put clothes in the dryer, and then you have to wait for them to be dry and then take them out, fold them, and put them away. My washer takes so long in comparison to my dryer. So my clothes are dry, I can fold them and put them away, and the washer is still not done. The washer controls how fast I can go through the entire process. So that's what's going to happen with a lot of our reactions. We're always waiting on that first step to occur before we continue on with the rest of the reaction. So whenever we said a reaction is first order or 0 order, so first order, they're kind of directly related. If something doubles, the rate doubles. If it's 0 order, the concentration does not affect the rate. Then we can have one like this, where it's A is second order and B is first order. So overall, it's going to be second order with respect to A, first order with respect to B, and then you can do an overall order by adding together those exponents. So this would be third order overall. If the reaction order that rate is positive, that means that the higher concentration, the faster the reaction rate occurs. If it's 0, the concentration does not affect the reaction rate. If for some reason that exponent is negative, we're not really going to deal with these, but they do exist. This is where as the concentration increases, the reaction rate decreases. This we're really not going to deal with. This a lot of times deals with some of those multi-step reactions or reversible reactions. If for some reason that exponent is a non-integer, this you're also not going to deal with. Those are more complex reactions. So those may be like a 5-step reaction that we're also not going to deal with. And finding the unit of the rate constant, this we just did in the previous reaction at the bottom. So the rate constant does depend on the overall order of the reaction. So to determine the value and units for K, we had to use data from one trial and sub it into the individual rate law. So that's where we plugged in the rate and the concentration of 2 substances, found our rate to be 200, and then we had to find the unit. So that's where we did the molarities. We're on our right side. Our left side, our rate was molarity per second. We divided to get that overall unit. So here's kind of another example, and we're going to walk through this one together as well. So here we have our base reaction. We have 2x plus y produces z. It gives us data with the concentration of x, the concentration of y, and then the rate of formation of z. And it wants us to determine the order with respect to each reactant, write the rate law, find K, and determine its unit. So the same thing we did with the previous one. In terms of rate law, we can go ahead and write our basic rate law. And then we just kind of have to fill in everything else. So our rate should equal K times X to some number times Y to some number. So that's kind of our basic form that we always use. Like we said, for X, we need to figure out where X changes, but Y does not. A lot of people automatically go for the first 2, but if you look at the first 2, X changes and Y changes. So where Y does not change is actually going to be these last 2. Here's where Y does not change, but X does. So you don't always have to pick the first 2 or even 2 that are right next to each other. So here, Y does not change, so we can use this to find X. It's the same thing, we kind of do the difference in concentrations, the 0.60 over 0.40 to some power is equal to that change in rate. So we have the 1.3 times 10 to the negative second over 8.7 times 10 to the negative third. So if we simplify that, and I'm not doing math in my head so well today. So 0.6 divided by 0.4 is 1.5 to some power. 1.3 to the negative second divided by 8.7 to the negative third is 1.5. So what would A be if they're the same number?
Four.
Yeah. So A is going to be first order. And then we can do the same, so X is going to be first order. We want to do the same thing with B, or with Y. So we need to see where Y is changing, but X is not changing. So I'm going to change color so it's a little bit more clear. So where Y is not changing can only be the second and third data points. So you can use the same data points for whatever you need to. So here, if we're looking at it, we have Y. The difference in Y is 0.4 over 0.20 to the B power is equal to our change in rate. So we have 8.7 times 10 to the negative third over 8.7 times 10 to the negative third. So 0.4 divided by 0.2 is going to be 2 to the B power is equal to 8.7 times 10 to the negative third divided by itself is going to be 1. So 2 to what power would equal 1? So that's going to be the one where the concentration changes, but the rate does not change. So that will be 0 order. So that will be a 0. So we determine the order with respect to each reactant. Sometimes they'll ask you to write this out. If you show the math, that's fine, but it may want you to say it's first order with respect to X, 0 order with respect to Y. The rate law, remember, is going to be rate is equal to K, and X we said was to the first power. Since Y is to the 0 power, we don't even have to include it. If you write it to the 0 power, that's okay. If you leave it completely off, that's okay too. Then it wanted us to calculate K and figure out its units. So I'm going to switch colors again. So that's where you took a data set and plugged it in. So like I said, I tend to pick the first one. You can pick any of them as long as you use the same data set. So I'm going to pick the rate. I'm going to do the first one. The 4.3 times 10 to the negative third is equal to K times 0.20 to the first power. So to get K, we would divide. So 4.3 times 10 to the negative third divided by 0.2. I get that K is 0.0215. And to find units, so remember we had molarity over seconds, and we divided by only 1 molarity because the exponent was 1. So we got rid of molarity, so this is 1 over second, or the second negative 1. Either way would be an okay way to write those exponents, those units. All right. So that kind of went through all the different pieces. Right now, does anyone have questions, or they're not sure how to do any particular part of a rate law? So confused on which 2 things to use on the chart. And here's the thing, it's not always the same 2 things. But you want to look and see, so for the purple was whenever I was figuring out X. So to figure out X, I need to see where Y is the same. So the only 2 data points where Y was the same were these last 2. And whenever I was figuring out Y, I need to make sure that X is the same. Well, the only data points where they're the same were the second and third one. So you really just have to look at whichever variable we're looking for. The opposite variable needs to not change. So let me see if I have another one that we can pick out. Okay, I do have another one here. So looking at this one, if we're wanting to figure out A, we need to figure out where B does not change. So we need to use either the first, third, and fourth. Well, the fourth, we don't have a rate law, so it needs to be the first and the third. Whoops. Sorry, I switched and my pen didn't copy over with me. So this one, B, is the same for the first one and the third one. So those are the points that we would use to figure out A. Because A changes, but B does not. Whereas if we wanted to find B, we would look for where A does not change. So A does not change between the first 2. So that's the ones that we'll use to find B. And this does just take some practice overall. So if you guys want to take a minute, you can try this one. Okay, confused on how to find the K unit. So I want you guys to find this one real fast, and then we're going to talk about the K. So for K, the rates tend to be in molarity per second. So it depends on what your rate law is. Say that this ends up being second order overall. Say that we have like A to the first and B to the first. You end up dividing by molarity squared because there's two of them. So one of them will cancel. So this is one where you kind of have to write out your units separately. So I want you guys to try this. See how far you can get. And we're going to walk through it together. I already picked the pairs for you. So that may help you. And we're going to go over this one. All right, guys, so we're kind of going to start walking through this. Even if you didn't finish, that's okay. We're going to see how far you got and kind of talk about some of the harder stuff like the K and the value, and then the rate of formation, rate of consumption. So that kind of goes back to that. One, find the order with respect to A.
Is it first?
Yep, it's first order. So whenever you do the 0.2 divided by 0.1, you get 2 to some power. The 1.2 times 10 negative fourth divided by 6.0 times 10 negative fifth also is 2. So power equals 2, so it's the first order. Did anyone find the order with respect to B? All right, so this one you're going to do the same process. So the concentration of B went from 0.2 to 0.1. So 0.2 divided by 0.1 is 2 to some power. And yet again, our rate, we have the 1.2 times 10 negative fourth divided by the 6.0 times 10 negative fifth. So that will also be 2. So 2 to some power equals 2. It's going to be 2 to the first power. So this is also first order. So both A and B are first order. So then it wants the overall order. Well, remember you add together your exponents. So if both of them are 1, 1 plus 1 is 2. So this is going to be second order overall. So our rate law is going to be the rate is equal to K times A was to the first order and B was also to the first order. So that's our base rate law. It then wanted to know the value of K. So remember, to find K, you need to plug in some data. So just pick one of the data points. I normally pick the first one. So we plug in for K, we plug in rate, or I actually need to plug in the number. So the number that I picked for the first one was the 6.0 times 10 to the negative fifth is equal to K times A, which was 0.1 to the first, times B, which was 0.1 to the first as well. So whenever you divide, you get that K is equal to 0.006. Now here's what Kim was asking of how do I tell the unit? So remember the 6.0 times 10 negative fifth is molarity per second is equal to K times molarity first, molarity to the first. So that's molarity squared. So whenever we divide, we have molarity per second times 1 over molarity squared whenever we're dividing. So that cancels out a molarity. So it's going to be molarity to the negative 1, second to the negative 1, or the 1 over molarity times second. It's two different ways to write them. The rate of formation of D in trial 4. So here's where, since we now know our rate constant, we know our K, we can plug everything into a rate law to figure out the rate of anything, so any trial. So for the rate of formation in D in trial 4, we would simply say, okay, the rate was equal to K, which was the 0.006, times 0.3 to the first, times 0.1 to the first. So if you plug that in, we get 1.8 times 10 to the negative fourth, and rates are in molarity per second. The last one is the one that tends to trip people up because they're like, I don't know. It doesn't tell me how much A is changing or anything like that. But remember that we had those rate laws earlier where we said that the rate can be stoichiometrically changed. So if we're looking at the rate of consumption of A, remember we said the rate of consumption is equal to, since it's a reactant, it's negative 1/2 because there's a coefficient of 2 times the change in A over change in T, which is our rate that we're given. So we can plug this value straight in up here to get our rate of consumption. So, or excuse me, plug it in here, not there, because we're looking for this rate of A is what our target is. So A is going to be used about half as fast as D is because it's a 1-to-2 ratio. Or excuse me, twice as fast because for every 2 moles of A, it's making 1 mole of D. So hopefully that helps you kind of figure out which data points to pick from, how to figure out the moles of, or excuse me, the units of K. Those are some of those things that you're for sure going to see that tend to come up. Right now, does anyone have any other questions, or it may just be that you need to practice this and try this and figure out where the issues are? Because a lot of times you can look at a problem and figure it out. And if you want, I do have another example that's on here, and I can leave it up and I can even give you the actual answers and see if you can get to it. Would that be helpful for anybody?
I have a question about the
Hey, Ann Lisa, you broke up. You have a question about what?
the last problem.
Okay.
So for the rate A in trial 4, what would like the units?
So it would still be molarity per second. That's not going to change. So whether it's rate of formation or rate of consumption, it's always going to be molarity per second. But since we're consuming A, it's going to be negative.
Okay.
Whereas here, the rate of formation is positive. And Addie had a good question. She said, so for first order, is the K unit always going to be the same, or does it change with different problems? Based off of the overall rate order, the overall order of the reaction, K is always going to be the same. So if it's a first order reaction overall, it's just going to be like 1/2 because the molarities will cancel. Whenever it's like this and it's second order overall, it's always going to have 1 molarity on the bottom. If it was third order overall, there would be molarity squared on the bottom. So based off of the overall rate order, the K unit will kind of be the same whenever you have the same overall rate order. Okay, so I'm going to stay logged on. I need to eat something. My blood sugar is dropping. I can feel it. I'm going to leave this up for you guys. You can try this one. Give me a couple minutes, then I'll put an answer up. But I have to put something in my system. If you feel like you don't need to practice or anything, you are welcome to log off. But other than that, we will stay on here.